Hello friends, we are continuing with the series of videos on HPC and cuda, and this is going to be the 15th video, shared memory example. This is the new concept where the array size is 16 now we are considering. So 16 elements additional example. So now you can see actually in any GPU there are streaming multiprocessors like we said in our GPU which we use, we have 6912 cores and also 108 streaming multiprocessors. Now you can see that there is L1 SMEM memory inside each streaming multiprocessor, and we have L2 cache also and also global memory. Now what is shared memory? Shared memory is the on-chip memory that is available to each individual streaming multiprocessor. Like in our case 108 streaming multiprocessor, each will have shared memory, and it is high speed memory as it can be placed very close to the SM and can be completely accessed by SM. For example, HPC GPU has I said 108 SM and total of it was like 6912 cores. I'm sorry, it is 1912 is not correct. 6912 cores, because on chip shared memory is much faster than local and global memory, and shared memory latency is roughly 100 times lower than the uncached global memory. That means in way it is faster. Now this is 100 times lower latency, means is faster, 100 times faster, and shared memory is allocated per thread block, and all threads in the block have access to the same shared memory. Threads can access data in shared memory loaded in global memory by other threads within the same thread block. Now, so shared memory on different devices, like on devices of compute capability 2x and 3x, each multiprocessor has 64 KB of on-chip memory. It can be partitioned between L1 cache and shared memory. For devices with compute capability 2x, there are two settings: 48 KB shared memory or 16 KB L1 cache and 16 KB of shared memory or 48 KB of L1 cache. By default, 48 KB shared memory setting is usually used. Now, there is a condition called race condition when using shared memory. It's like two people trying to access same location. When sharing data between threads, we need to be careful to avoid race condition. Let's say two threads A and B, each load a data element from a global memory and store it to the shared memory. Then thread A wants to read B's element from the shared memory and vice versa. Let's assume that A and B threads are in two different paths. So if B has not finished writing its element before A tries to read it, we have a race condition. So now we straight get into the program. So what is the difference in shared memory programming and in the normal programming? Now in the shared memory program, when we are talking about 16 elements, the array size is 16, and we have to define whatever is marked in red is something additional from earlier videos to make it shared memory compatible. Threads per block you define here as 16. Now inside the function, like you are creating the kernel add array shared A, B, C, that is what will be passed in from the CPU, and shared integer shared underscore A. These are the syntaxes which you have to use for A and B, which was not the case earlier. IDX is calculated like earlier only. Now this red line, if IDX is less than the array size, then you have to say a thread IDX x is equal to, you are copying the values a and b, so that you are within the array size, and sync threads. And this is how, these are the extra lines which are required to be implemented while doing the shared memory example. Remaining lines are exactly same: allocation, memory copy, etc., etc. The final result of this is shared memory example.cu. Looks like that. And what we will do is, we will do a compiling of this in the real machine, and also we'll try to profile it also once and see how it is going to be. So I am going into the remote system, where the HPC system, we are going to now srun -n, 1 means one node, and GPU minus gres is equal to GPU 2. This is a standard command we have been doing all throughout. So after that, you CSQ command to see the node allocated to you. $user is your username. So you are allocated with RP GPU 003. Now next command is like module load spec. That is, spec is to be loaded to install any program. So you go to you just cut and paste the environment syntax. After that, now you are ready to spec load cuda. Now the next command is very important, like you have to put the version along with that. Just cut and paste the string from here, then put it. Now you can simply run this. The program is here, shared memory example.u. Then you can simply quit and run this nvcc shared memory example.cu. Creates a.out. We will see what is inside this. And we also do a quick profiling. Output is correct, so which is also not a bad idea to do the profiling also, to see how much time it takes. So we have done this. So we are going to get a report which will take it to the Windows machine. And it is report 7 has been done, and through win SCP we can simply drag in from the right side HPC to the local Windows machine, and simply open that file to open in NVIDIA Inside Systems in Windows. We want to just see how much time it took. So it took very less time, 1.984, even less than when we did a 3-element addition earlier. We were taking almost 2.5 microsecond. Now it is taking even less. So it is a good example. So thank you, and wait for the next video. Thank you.